Good evening, everyone. Hope you're having a fantastic week as always. How about we jump into it, eh? We're working through the Cryptopals series at the moment. If you've missed the last couple of streams, there's a YouTube link somewhere down below. If you're tuning in from YouTube, hello to you. We're on I'm calling it part 3, but it's the 4th episode in the series because I decided to try to be smart and call one of them 1.5, and now it does my head in every time I think of which episode we're up to. But we've worked through the first couple of challenges here in Cryptopals, working through things like single byte XOR ciphers, detecting them. Pretty sure we broke them. Detect single character XOR, we broke it, didn't we? Oh, we had to pick the needle out of the haystack. That's right. So this was building and breaking. This was breaking a whole bunch all at once, and that gave us some trouble. And then we worked through implementing repeating key XOR, and how that works is you take a plaintext, you take a key, and then you cycle that key and you repeat it over and over again, and then you pair the characters up one by one, a byte of the key with a byte of the plaintext, XOR those together. That's a byte of your ciphertext, and you work all the way through your plaintext, looping through your key until you've encrypted the whole lot. We are now working through breaking that exact cipher scheme. We've been given a file, which is a base 64 WAD. We decode it to get the ciphertext, and we're told that that is some ciphertext that has been encrypted with one of these repeating key schemes. We don't know what the key is, of course. We also don't know how long the key is, and we then need to break the cipher. We need to find the key and recover the plaintext. So we're working through this, and the first step to doing that is to discover the length of the key. And the way in which we did that last stream was with a mechanic called Hamming distance. More specifically, Hamming distance on a bit-by-bit basis. The Hamming distance is essentially how many bits in one thing, one stream of bytes, you need to flip to be able to get the other stream of bytes. So it's not which bits you need to flip, it's just how many of them, how many bits difference are there. It's kind of almost a measure of entropy, but again, I think I'm using that word incorrectly. Barney, are you talking about Hamming distance? It's a strong name, isn't it? It's a good name. If you're not talking about that, what is it that sounds like a good song name? So what we were doing with the Hamming distance is we were chunking... Oh my god, I just realized. I think this is the first stream I've ever had where my ears aren't too loud. That's incredible. We use the Hamming distance. We break... Yeah, that's right, Barney. We broke the ciphertext up into chunks of increasing size. So first of all, we split it up into chunks of size 1, and then chunks of size 2, and then chunks of size 3, and so on. Until we got to what did we say? It gets to about halfway through. Yeah, we're not going to split it any more than we don't get at least 2 full-size chunks, right? For each of the different size chunks we'd break it up into, we would calculate the Hamming distance between each chunk and each other chunk. We'd kind of do the handshakes at a party problem where every chunk gets compared to every other chunk, which gets out of hand quickly, as this is quite slow now. Calculate all the inter-chunk Hamming distances for each chunk size, and then normalize them and divide by the chunk size and divide by the number of chunks that we compared against each other to get kind of like a measure of, again, entropy between in the case of chunks of size 4, we would know how much things seem to be changing bit by bit between each chunk of size 4 and size 5 and size 6. And it works out that once you start chunking stuff at a chunk size that is the key length, the Hamming distance goes down quite a bit. And that's because once you've kind of broken it into chunks and then lined all the chunks up and they're all the same size as the key's not doing that much damage to it anymore. it all kind of averages out in a way, sort of. It makes sense in my head. I hope it makes sense for you. The crazy thing was we also found that all the multiples of the key size also tended to have quite small interchunk Hamming distances. So there's some really wild stuff going on in here as to how we kind of get our results and decide what is the smallest chunk size that seems to have a good Hamming distance. It's never going to be perfect. It's never going to be like 0, but how do we kind of decide what number's small, what number's big? I'm not good at stats. It is what it is. And that seemed to work. And surprisingly, it also seemed to work once we encrypted a whole bunch of text from Alice in Wonderland, the first 2 kilobytes of it. We encrypted that with a key, which was just, you wouldn't batch an RPC call, because of course you wouldn't. And it was able to figure out the length of this key, which I think is pretty cool. So that was last stream. Now we need to work out what to do with this. We kind of feel like we're part of the way there. We know how big the key is, this repeating key, this repeating unknown key for the ciphertext we've been given, which is this mess here. We know the ciphertext, we know how long the key was. Now we need to find out what the key is. Barney, did I do spaces? In what sense do you mean did I do spaces? You might be thinking of something we did 2 streams ago when we were kind of trying to judge the Englishness of an arbitrary input. Because we were thinking of kind of rewarding spaces in that case. I didn't end up doing it. But I'm not sure what you mean by doing spaces in the context of the repeating key bizzo. You've been in and out. Yeah, cool. So yeah, no, we didn't end up doing that. We got to the stage where we had to just move on with our lives. We'd spent way too long on those challenges already. But the code is on GitHub. There's a link down below somewhere, whether you're on YouTube or on Twitch. If you'd like to give a go, have a go at catering for spaces in my Englishness function, knock yourselves out. That sounds like something I don't want to do. I've had enough of that code. So what are we going to do now that we know the size of the key? We know that it's probably 29. That's what this function we wrote with the Hamming distance. Oh, one thing I thought of while I was off stream, I want to rename this function from bitwise Hamming to bitwise Hamming distance. I think it's just a little bit more correct. So I feel better about that now. Let's do key length equals guess repeating XOR key length over the ciphertext. I'm pretty sure it's 29, but we'll calculate it dynamically and burn a bunch of CPU each time regardless. Actually, you know what? Let's not burn CPU time each time we do it. So we're going to run this function. Main just opens up the challenge input, reads it, base64 decodes it. We don't need this key size stuff anymore. Main then calls break repeating key XOR. That makes sense. Cool. Which is going to get that key length and print it out. So if we run this, you can see it's quite slow. And I don't want to sit here waiting for this to run each time. So now we know that it's 29. Let's cache that value. Key len equals 29. So that way we've hard coded it in there. When we're done with the challenge, we'll uncomment this to have the whole thing run properly. But for now, look at that. Heaps fast. So we've got our key length. Now I want to Barney registered official Justin Stephen on Twitter and it's verified. Yep, Barney's still speedrunning the Get Banned challenge. Good to see. If nothing, you are consistent, my friend. We now want to chunk our ciphertext into 29 byte long blocks, which we just did some chunking up here. And even though it's one line of code, here. It's kind of ugly line of code. I'm inclined to, do I want to factor that out? Yeah, I think I want to. I don't think this is the expensive part of this function. I think the expensive part of this function is in the itertools.combinations. Like this is going to spin and spin hard. Let's refactor this chunk code out. Def chunk. It's going to take B, which is bytes, and it's going to return list of bytes. All we do is return. Don't need ciphertext. That needs to be B. And we need a chunk size, which is int. Cool. So this function here basically just splits B into chunks of size, chunk size. Let's get a little bit, do we want to get fancy? Do we want to get fancy? Let me have a think about something. Chunks is that. I was going to consider, yeah, we might need this function in future challenges. So we should take the time to do it well, which means writing some tests. We're going to chunk A, B, C, D with a chunk size of 2, and we expect to get A, B, C, D. Now our doc tests are getting kind of slow. I'm inclined to start commenting out some of our doc tests so that running this test suite doesn't take forever. I'm going to start with this guess repeating XOR key length because it is really slow. I'll stop the tests, rerun them. That's fast enough. I'm happy with that. And this test passed. Hooray. Let's write another test. Let's do ABCDE with a chunk size of 2 because we expect to get that lonely E at the end there. Awesome. Now, in terms of getting fancy, what I want to do is instead of returning a list of bytes, I'm going to return what's called a generator or an iterator. I think those words are interchangeable, but I don't know. That is to say, rather than, let's say B was like a megabyte. So the caller to this function, the caller has a megabyte already in memory. And we're going to chunk it 5, 6, 7, 8 bytes at a time. It doesn't matter. Right now we're returning a list, which is basically that megabyte. Did I say megabyte? I think I said megabyte. Let's make it a gigabyte. Let's get crazy. Let's say B is a gigabyte. The caller already has a gigabyte in memory. And us being chunk, building this list in memory and returning that whole list is another gigabyte plus overhead for the whole list structure. It's a lot of wasted memory if the caller doesn't need a list. If the caller wants to work with these chunks one by one, maybe it just wants to be able to say to the chunk function, hey, give me the next one, give me the next one, give me the next one. Rather than getting it all and then going, cool, now I've got to go dig through it. Thanks, I hate it, right? Take, for example, the function range. If you do range 5, you'll see you get this weird thing back that it just says range 0, 5. You don't get all the numbers back. If you want all the numbers, you can do list of range of 5, and it does what's called, what I call realizing that iterator in memory. It kind of asks it to exhaust itself and bundle itself up into a list, and in memory there it all is. So you can do things like this. You can do for I in range 5, print I. This part here didn't actually create a list in memory. It was just the print was like, give me the next one, give me the next one, give me the next one, which in the case of this is kind of boring. But, you know, for I in range 1,000,000, print I. All right, that made me look stupid. 0, 0, 0, 0, 0, 0, print I. You can see that it pretty much started immediately. Whereas if we were to do for I in list of range of 5, print I, if you look carefully, maybe this will lag a little bit. Maybe 1,000,000's not big enough, but maybe this will lag a little bit. Nah, didn't lag at all. 100,000,000? See that lag there? Then it goes. Do it again. Because we're realizing that entire 100,000,000 or whatever I said in memory. Enter. There it goes. It took like a second to actually build that huge list in memory. If we just got rid of the list part and didn't realize it before we started, I'm going to press enter and this will start immediately. Bang. Nope, bang, there it is. Do it once more. Bang. All that is to say, generators and iterators are super cool. They're much gentler on memory when the caller just wants to work with one thing at a time. They're just nice. How do we make a generator? So the docstring, well, I'll play the docstring first. Split B into chunk size. Split B into chunks of size, chunk size. Let's change this to yield chunk size chunks from B. Kind of better describes how a generator works. Instead of this list comprehension stuff, what I'm going to do is, for I in the range 0 to the length of B, stepping by chunk size, yield B from I through to I plus chunk size. This magic word yield is what is basically causing this function to be a generator or act like a generator. The caller is going to call into it. This is going to execute. It's going to start up the loop. Python's going to see the yield word, calculate this, and spin it off. And then kind of like save its state in a way. And then the caller, when it's like, okay, I want the next one now, it's going to re-enter this generator and say, give me the next one. The state has been saved. This loop's already done one iteration. It's going to yeet the next one and save its state. So yield's a super cool, powerful word. This test will now fail. If we run it, we get errors. Because instead of getting our list like our test said we would, it's getting this yucky generator. We can fix that by just wrapping it with list. To kind of say, realize it all for us. Run the tests. They run clean. Barney, do I still use pwn tools? Absolutely I do. It doesn't have much of a place with what we're doing yet. Maybe it will, maybe it won't, I don't know. But yeah, I love pwn tools, it's amazing. Last thing, we're building a generator. This function no longer returns a list, and I forget the type hint for generator. Is it just iterator? Generator, yield type, send type, return type. I think these two are normally none. Yeah, you can see here, generator of int none none. Send type and return type, I'm sure they're used for like advanced generators. Not that I've written a lot of generators, but I haven't written a generator that uses these yet, I don't think. But I'm sure they're there for good reason. This function returns a generator, which spins off bytes, none, none. Pull that name in, generator from typing. Cool. Got a beautiful chunk generator. So we can replace this here with a call to the chunker. So chunks equals chunk of ciphertext with chunk size of chunk size. That's right, isn't it? Yep, ciphertext, good. Now, all that hard work in building a generator, and I'm going to immediately realize this list. Because we need to be able to run length on it, and we need to then have itertools.combinations kind of shuffle and reshuffle and reshuffle our chunks. And generators don't work in the way that we're using chunks here. So we'll kind of cast it to a list or realize it in memory. And I expect the code we're about to write down below is also going to do this. But I just think chunk, just in case for later. We're probably not going to need it, but it's nice that it's a generator. Let's rerun this test to make sure we didn't break it. Uncomment it. Run the tests. That is a beefy test case or test suite. So that is good. We did not break it. We'll comment those back out. Okay, so we've got our cached key length. Right, chunking. Chunks. We're again just going to cast it straight to a list because we want to kind of play with it as a full list in memory. Maybe we can get rid of this call to list later, but for now, I'm going to realize it. So we're going to do list of chunk of ciphertext with the chunk size of key length. And let's print. Let's do chunk in chunks. Let's come back to this. My name is Tito. Welcome. Good to have you here, my friend. What are we coding? We're working through a series called Cryptopals. So, in the previous stream, we implemented what's called repeating key XOR encryption, which is to say we take our plaintext and we encrypt it using XOR with a key. So we built that encryption function, and now we're breaking it. So we got given this big, awful base 64 mess, which represents the ciphertext of some unknown to us plaintext encrypted with an unknown to us key. We have to break the key, decrypt it, and get the plaintext. So hopefully that fills you in on where we're at. Why is my chunk angry at me? There's a function called chunk. What's your problem? You got to work out what key type it is. Not really. We know the key type. It will. If we go back to the previous challenge, the key is going to look like a word. And the XOR is a very, very primitive basic encryption scheme. So we're not talking AES or RSA or anything like that. They come in the later challenges when we've got to crawl before we walk. XOR is like, Babby's first encryption. Not too technical. Well, it's fantastic to have you here. Please let me know if you've got any questions, and I'll do my best to help out. Meanwhile, my IDE is yelling at me for some reason. What if we just run this code? Chunk reference. For chunk in chunks. Is it because of this line here? Yeah, so I'm like reusing the word chunk. So maybe that's a bad function name actually. Let's rename this. Chunkify. That sounds more like a verb than chunk. Let's call it chunkify. I do a little bit of stuff for Cloudflare, that's about it. Cool, what are you doing for our Cloudflare? So I got chunkify, yep, that one got fixed, good. Okay, so for chunk in chunks, print chunk. So I'm going somewhere with this. Let's run this. And that looks like awful output. Let's hex those chunks. I still don't love this output. Let's print space.join O2x format B for B in chunk. So this is a bit of yucky code to just print things the way I can see it in my mind. That's what I want. Some spaced out hex bytes. Okay, so we've broken our ciphertext into chunks of size 29. Yeah, 29, because that's the key length we've worked out, right? So here's the first chunk, here's the second chunk, here's the third chunk, and so on. The first character of the plaintext got encrypted or XOR'd with the first byte of the key. The 29 plus 1th also got encrypted or XOR'd with the first byte of the key. So did this one, so did this one, so did this one. All of these bytes were encrypted with the same key byte. Same for the second one. This 42 is the XOR of the second plaintext byte with the second key byte. This is also XORed with the second key byte, second key byte, second key byte, second, third. So if we look at these rows of hex values and kind of transpose them and look down the columns, each column is the result of kind of like single byte XOR. Now we're only going to be getting stripes of the original text, but even a stripe of the original text should still obey the English character frequency rules. So if we brute force this first column as though it was single byte XOR material, same for this one, same for this one, same for this one, and apply the English character frequency rules, it's kind of like a divide and conquer problem at this point. We can recover the key, and we can recover the plaintext one stripe at a time, and stitch them all back together. Like, tell me I'm wrong, right? So, one thing I'm noticing is we do have like a leftover chunk, a leftover handful of bytes at the end here. Which might not be a problem. It just means that the first, second, third, fourth, and fifth stripes that we divide and conquer and brute force will be 1 byte longer than all the rest, and that's fine. I think the first step is kind of like transpose, divide and conquer, discover the key, and then just decrypt the whole thing with the key that we established. I think is probably the safest way to code this. So now how do you transpose lists in Python? That sounds like something I should know how to do. But I don't. Transpose lists Python to Stack Overflow. Okay, we're getting NumPy and pandas. That feels... it would work, but it feels heavy-handed. Transpose list of lists. List map, list zip, great. Zip. Zip. Hold on. Zip. Eccentric, how are you not following already? Welcome, my friend. I haven't seen you since forever, dude. So good to have you here. quick recap for Eccentric. Breaking repeating key XOR. We got given this mess here. Need to base 64 to code it, and it represents something that has been, it's some plain text that's been XOR encrypted with an unknown key. Kind of like this. Here's some plain text. If you encrypt it with that key, you get this. We've done this challenge already. Now we've got to figure out the key. So we've done the Hamming distance trick and the chunking trick to find the key length. And now we've got to transpose this jumble to kind of divide and conquer, brute force the stripes of a key at a time using English character frequency tricks, which we've already fortunately written a lot of the code for in the previous streams. So now we've got to transpose and then throw stuff at our old functions until plain text falls out, fingers crossed. I'm just trying to remember how to transpose a Python list of, I guess they are list of lists. Let's do A, B, C, D, E, F, G, H, 1, 2, 3, 4. Okay. If we zip A, I don't know that this is going to give us what we want. What if we zip star A? Did that just work? What's hex 49? That totally just worked. Thank you, Stack Overflow. So it's ugly. If we do bytes x for x in, there we go. We've got the first byte of each here, the second of each, BF2 here. Cool, cool, cool. What if we had like uneven stuff? So chuck a Z here, chuck a Y here. AE1, BF2, CG3, DH4. Okay, so we lost the Z and the Y in this trick here. Zip longest does not discard any data. Editors.zip longest, is that going to fix this? Nope. That because it fills stuff in with none. Yeah, so we get a none hanging out at the end there. So I think A is a tuple. Does A have R strip? No. This is getting kind of ugly. I don't think that's what we want. How can we tidy up this none cheaply? That's not what I wanted. That's not what I wanted either. How do we... Let's just grab that. Doesn't give us much, does it? What if we look at the documentation for zip longest? Fill value equals none. I think this is what I want. 11, 12, 13. Yeah, this looks fairly reasonable. Okay, so we get given code for what we want. That's... okay. That's kind of yuck. Zip discard, iterables, sentinel, turn map, partial, gross, gross, gross. Not loving it. Of course we can't do bytes over X because none blows up. B for B and X. If B is not none. Kind of gross, but also kind of works. Bytes of B for B in X. If B is not none. For X in the list of... What are we listing that for? Of course. Oh, I overwrote A at some point. Good on me. There we go. So this transpose gives me AE1, BF2, CG3, DH4, and then the short chunk at the end, ZY. Ship it. Sorry if that didn't quite make sense. That it's one of those things where you just fudge it till it works. What did I just do? Chunks. Chunks transpose is that right? Over star chunks. Get rid of our printing code here. Simp Crusader understands pink poker lingo. Welcome, Simp Crusader. Good to have you here. Actually, you know what? Let's bring that back. Dash, dash, dash. And then do this again for chunks transposed. Run this. So here was our original thing where we chunked the ciphertext into 29 byte chunks, and then the first stripe is 1D 36 7827. 1D36. Good. 7827. 7827. So here's the first stripe all the way down the left-hand side. Second stripe, third stripe, fourth stripe. So the first 1, 2, 3, 4, 5 stripes should be longest. 1, 2, 3, 4, 5. Yep. The rest are short. I think we've successfully transposed it. I'm calling that good. Comment out our printing code. Now, we just attack each of these as though they were single byte XOR encrypted stuff, right? Which we wrote a function for previously. Break single XOR cipher. So how this works from a previous stream. Oh, that's right, it takes a list of ciphertexts. That's fine, we can fix that. For each of the possible keys, because remember, a single XOR cipher has a key of length 1. And I don't have a function for it. That's fine, that's fine. So for each of the possible 256 keys, do the encryption with that key to try and undo the XORing. So you're brute forcing, and then we're building a list of decryptions, and we're scoring it. And the score is given by this scoring function, which by default measures the Englishness of the output, which is like checking to make sure that E is about the 12% most popular character, T's make up 9%, A's make up 8%, O's make up 8%-ish. It's giving the plaintext a score based on the table of character frequencies. And then it's like our single XOR cipher breaking function is returning all those possible decryptions sorted by the score, with the most likely decryption being first based on character frequencies. Cool, so we've got that function. We should be able to for chunk in it's a transposed chunk. For transposed chunk in chunks transposed, it's a bit of an awful. Let's rename this to transposed chunks. So for transposed chunk in transposed chunks, start building a key array, which is just going to be a list of integers. Key.append, break the single XOR cipher over this transposed chunk. We'll use that default scoring function being the Englishness. Let's cross our fingers that our ciphertext is big enough to give us an accurate read. We'll pull the first result off that list, because remember it's sorted with the winners coming first. So we'll pull the first one off, grab the key. I really hope this works. This function takes a list, that's right. Because we were fancy and removed redundancy from our code. So again, we're working through each of our transposed chunks, and we're just building this key, and we're kind of YOLOing it, hoping that this function can work against ciphertexts of this length. Just grabbing the key from the first result, building a key list, crossing our fingers. And then let's just print the bytes of key and see if it looks like a real key. I just want milk that tastes like real milk. Terminator 10, bring the IOIs. I think that's pretty damn close to a key. I don't know if it's Terminator 10 or Terminator X, but I know Mac OS X is Mac OS 10, so I'm calling it Terminator 10. If I'm wrong, let me know in chat. That looks like a key to me. I think this character here is probably wrong. Probably bring the noise. That's damn good. Here's what I'm going to do. Clean this up, clean this up, clean this up. I'm going to uncomment this now. I'm going to slow things down and actually run the XOR key length guessing function. This function is no longer going to break the repeating key XOR. Oh, it is going to break. It'll break it. But let's write some documentation to clear up what we mean by breaking. Return the best guess key for a ciphertext which has been encrypted using repeating key XOR. I'm going to get fancy, and I'll probably regret it. This function can take a key length of optional integer. By default, it's none. So if the caller to this function knows the key length, they can give it. If the caller to this function doesn't know the key length, this function will work it out for you. I think that's nice. How do I like actually do my doc string now? This is getting kind of gnarly. There we go, add parameters to docstring. I don't know which docstring format I normally use. That'll do. I'm going to add some documentation about what the parameters mean, just because this function is getting a little bit wild. Ciphertext. The encrypted ciphertext. Key length. Optional. The key length, if known. If unknown, interchunk Hamming distance will be used to derive it. Now, here's an ugly bit of shorthand. Key length equals key length if key length. No, I'm not going to do that. If key length is none, key length equals that. Fix up that key length. Cool. So yeah, when this function runs, if the key length wasn't given, go and work it out. If it was given, then this value gets used when we chunk stuff. Now this function is going to return the best guess key, so it's got to return bytes, so it doesn't have to print the key, it just returns the key. Good. So this is no longer a res, it's a key. Guessing key for ciphertext, ... Got key. And we'll wrap that in quotes. Alright, so we'll run this now because this break function is just getting us the key. Guessing key for ciphertext. If got, Terminator X, bring the IOIs. Decrypting ciphertext, ... Now, fixed up key. Let's go and fix this key up because I'm pretty sure it's got a typo in it. Not a typo, but we just failed on one of the bytes. So I think instead of IOIs, it's probably going to be noise. As an analyst, we can make that good guess. Plaintext equals repeating key XOR of the ciphertext with the fixed up key. I just realized this function, repeating key XOR, it's got an argument called plaintext. Really, that could be plaintext or ciphertext. It should be probably called input, because remember, XOR ciphers are it's like perfectly symmetrical. But anyway, we can deal with that later. We got plaintext. Now this is going to be bytes. I'm going to guess we're going to be getting real text out of this. So I'm just going to YOLO decode it from bytes to a string and run. And if this works, I think we get confetti. That's looking pretty good to me. I'm not seeing any typos in it. Nothing jumps out at me, so I think that the key was indeed noise, not IOIs. There it is. That went way better than I thought it was going to go. Way better. So what have we done? We've guessed the repeating XOR key length with our chunking and our Hamming distance stuff, and then some ugly stats theory to pull out the best looking thing. We've broken the ciphertext into chunks of the length key length, transposed them, and then brute force them stripe by stripe. Attack all the first characters of each chunk, all the second characters of each chunk, all the third characters, as if they were just encrypted XOR single byte English text. Got the key, got the plaintext. It's pretty cool. I'm going to take a quick 5-minute breather. I suggest you stretch your legs, grab a glass of water, do what you need to do, and I'll see you on the other side. And we're back. Onwards to the next challenge. What have we got? AES in ECB mode. Brain broke. So we've got some base64 encoded content in this file. It's been encrypted with AES 128 in ECB mode with the key yellow submarine. Decrypt it. You know the key. Easiest way is to use OpenSSL cipher and give it AES 128 ECB as the cipher. Let's not use that. I think this is a bit of an old guide. There's now some pretty good Python cryptography libraries that are going to give us AES 128. But let's give this a go. Actually, before we do that, let's refactor this. Let's send some stuff to util. Bitwise Hamming distance, I want you, so I'm going to yoink you to util.py. Chunkify, I like you as well. We spent a lot of time making you a generator and then not using it. Off you go to util. Guess the repeating XOR key length. Yep, I like you. You can move to the utilities. Break the repeating key XOR. Is that function named okay? Gives us the key. Yeah, it's fine. You can go to, nope, you can move to util. Actually, that's the function I wanted to have a quick look at. Chunks equals list. Do we need to realize this list? Maybe we do. We're about to do a star operator on it. I mean, it's going to end up as a list. Maybe it won't end up as a list. If we just get rid of this list bracket stuff, can we avoid realizing that in memory? And then we run our challenge 6 again. Cool. we did use our generator as a generator after all. And then this here looks fine to me. We didn't write a test for... Wrong function. We didn't write a test for this function. We probably should. Let's move that back to... Stop it. Let's move that back to S1C6. Just so I can do some copy pasta. What are we going to do? Let's yoink that. Plop it there. So ciphertext equals, let's do open data slash s1 c6.text. Yeah. Okay, so we've got our ciphertext. And when we break it, we get back this, but with a typo in it. It was IOIS. Now, bit of a weird test, but at least what it helps us do is if we do change code in the future, it'll tell us if it breaks or not. Mind you, I'm about to comment this doc test out anyway because it's so dang slow. But we'll just check that it works, and we know we can always bring it back to life later if we want to run a full test suite. Okay, test passed. So if we comment that out, is our tests now not stupid slow? That's pretty quick, I'm happy with that. Alright, break repeating key XOR. You can go back to the utilities. We're done with you now. That looks fine to me. Okay. Homework done, maintenance done, house cleaning done. Let's move on to S1C7. AES ECB. Set 1, challenge 7, AES ECB.py. Grab our boilerplate. Can't type. Alright. Grab our challenge text. We need to grab our challenge. There it is. This is S1C7.text. Beautiful. And we're good to go. So in main with open data slash S1 C7 ciphertext f.read, encode it because base64 is picky. And decode it. Pull in base64, fix the typo, print the ciphertext, run it. Looks like ciphertext to me. We'll go with that. The key is yellow submarine. And the key is probably bytes. It's probably bytes. Now we need to AES 128 ECB it. for which we will reach into the Python cryptography bag of tricks. Cryptography.io, I think, is the modern day Python crypto library. pip3 install cryptography, I can do that. Let's jump into our virtual environment. pip3 install cryptography. Easy peasy. We've now got everything in the kitchen sink. Now we need to figure out how to do AES with it. Symmetric encryption, that's what we want. Now, what's kind of cool about the Python cryptography library is I just love this idea. It's got a module called HAZMAT, or Hazardous Materials. Whenever you're doing code review, you should be very wary if you see someone doing Python doing from cryptography.hazmat import blah 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 blah, because that means they're grubbing around in the code that, you know, like the classic advice, don't roll your own crypto. People who roll their own crypto bolt together stuff in from within the hazmat area of the library. You know, it's kind of one of those, if you're using it, you better know why you're using it kind of things. Point being, we're being asked to work with AES ECB, for which there's a beautiful meme. All modes are beautiful, not you. Yeah, I love this. You know, all cipher modes are beautiful, not you, and deserve to be used. Yeah, ECB is the don't use it of the block cipher modes for reasons why we'll find out soon, I'm sure. Hence, it's tucked away, along with a lot of the other AES stuff, in the HAZMAT module. If you see someone using HAZMAT, you should probably just check to make sure they're okay, they know what they're doing. There's often not a good reason to be digging into HAZMAT and using it. It's there for completeness and for when you really need to get down and dirty with like legacy systems and old data and that sort of thing. But in general, stay away from HAZMAT. It's the same thing as there's two other ones that I love. There's React. You know, HTML and JavaScript have always had the set in a HTML function. React basically renamed or named their equivalent dangerously set in a HTML. So A, it's like a reminder, whenever you're using it, as you type dangerously set in a HTML, you kind of think to yourself, ooh, maybe there's a better way. Maybe I shouldn't be using this function. Hint, you shouldn't be using that function. It often leads to cross-site scripting. And there's one more as well that escapes me right. Oh, I think it was GitHub. Same but different. GitHub Enterprise, their virtual appliance, like the hard drive was encrypted with a key, and the key was, dear reverse engineer, we know you're reading this key. We know that this encryption is not stopping you from reverse engineering the product. That's not the reason for this key existing. The reason for this key existing is to tell our customers there's no user serviceable parts inside. Don't decrypt the disk and start mucking around with your virtual appliance because you'll probably break it. You're welcome to. It's not supported, and this is your warning, which is just kind of like using function names or values as kind of like signposts, which I'm just a fan of. I think it's cute. HAZMAT, great idea. Dangerously set in a HTML, great idea. Sepkov, when did you start streaming again? I started in cybersecurity with your videos on YouTube. That was years ago when I was in high school, but I'm glad I got to catch you on stream. I'm your hero. Thank you very much, Sepkov. That's beautiful, and I love to hear it. I started streaming again within the last week or so, and I'm like speedrunning the Get Burnt Out challenge right now. So this is like my, I think, 4th within about a week. I will certainly not be keeping up that cadence, and I will be taking time off over Christmas. And I very much want to be back next year, but I'm a terrible streamer. So we'll see how that goes and how long it lasts. But for now, I'm having a great time. I'm really enjoying this, and I hope you do too. Thank you very much for tuning in, and I'm glad that you could catch the live stream. And thank you very much for your kind words. That means a lot to me. All right, let's play some Hazmat. Apparently we can do from this, import cipher, algorithms, and modes. Create a cipher with the algorithm being AES over a key and the mode being CBC over an IV. You know what, I'm just going to yoink this and we'll play with it. Gross. Better. I'm going to yoink this import and put it up here. I'm going to yoink this cipher. Cipher equals cipher algorithms.aes over the key, yellow submarine, with the mode. We're not doing CBC. Let me see if we hover over this here. CBC takes an IV. We are doing the don't ever use it ECB mode. Oh, don't tell me. Oh, we just need to call it, I think. I was going to say, don't tell me they ripped ECB out. And ECB takes no arguments because there's no IVs in ECB mode. And does this challenge say so? No. ECB is what's known as electronic code book. In fact, let's quickly look up ECB. AES ECB. Block cipher modes of operation. Because the mode is to do with block ciphers in general, not just AES. How does ECB mode work? So, okay, first of all, what is a block cipher? As far as I know, a block cipher operates on blocks. As opposed to repeating key XOR. Because ICE like repeats itself forever, right? So in a sense, repeating key XOR is like a stream cipher. Bytes go in, bytes go out, magic happens, ciphertext comes out the back. Blocks, you need to explicitly operate on blocks of plaintext at a time. And in the case of like AES 128, the block size is 128 bits, I'm pretty sure. So you chunk your plaintext into blocks. We don't need to do our chunking. I'm pretty sure cryptography is going to handle it for us. But you get a block, and in ECB mode, the key goes into... And my brain just broke. How does ECB work again? Wait, how does ECB work? Looks like when you put like the key into ECB, into AES, you get like a block of noise. Plaintext gets XORed with the noise, out pops the ciphertext. For the next block, I'm guessing this block in the middle is always the same for ECB. Does that sound right to anyone else? Plaintext gets chunked. This in the middle is constant. Out pops ciphertext. Because the main problem with ECB is if you've got, like, let's say this block of plaintext is exactly the same as the third block of plaintext. The common problem with ECB is this block of ciphertext will also be exactly the same as that block of ciphertext. And there's like a classic Tux ECB. There's a classic demo of this. The ECB penguin. If you get like a bitmap image of the Tux penguin and encrypt it with ECB, this is what pops out. The colors have all changed, but clearly where there used to be a run of the same color, the same noise has popped out. And if you don't even need to squint, you can see it's a penguin. You don't know what color the penguin was, but you know it's a penguin. You can see the outline of it. Anyway, that's the main problem with ECB. I'm failing a bit to articulate Like, it's kind of blowing my mind how these blocks in the middle work, but they must be constant each time. It's just that the plaintext goes in. I'm pretty sure these are just XORs here. If I'd scroll down like 2 centimeters, there's the penguin, right? So if you encrypt it with ECB, you get this. If you encrypt it with any other mode, you actually do get noise, so you don't get that repetition problem. Like when you go to CBC, cipher block chaining was kind of like the solution to ECB being horrible. It needs the IV and it gets mixed into the plain text, and then this block cipher with the key going in poops out a block of ciphertext, but that block of ciphertext gets mixed into the next block of plain text before the encryption. So you kind of get this like weird wormy pattern going on where it kind of, the output of one block feeds into the input of the next block to kind of further scramble stuff, so you don't get that repetition problem. Hey there YouTube, I goofed my explanation of ECB pretty bad right there, and after the stream I had a think and I realized the way in which I was thinking about things wrong, and it was causing me my confusion, and so I wanted to record this quick little bit right here to try to do a better job of explaining ECB. So this is ECB block mode cipher description take 2. It's this diagram here that really sent me for a spin. And it turns out what I was doing was I was trying to think of a block cipher as though it was a stream cipher. And spoiler alert, you cannot do that. Block ciphers and stream ciphers are very, very different in operation. So I was thinking that this layer in the middle here, that the AES machine was kind of producing a stream of bytes with which the plaintext was being XORed. I thought there was like an implicit XOR here. Turns out there's no XOR drawn there for very good reason. And I was kind of going, well, if plaintext gets XORed with the key stream, stream means stream cipher. I should have known. I was completely on the wrong track there. I was like, plaintext, if that's the same, then that's the same. I know that's the same, and then that's the same. Like, that's the problem with ECB. But I was like, why is the key stream the same the whole way through? Why does it like repeat itself? And it turns out that's not how block ciphers work at all. Like if you scroll down a bit here, this is how CBC works, and you'll see these little circles with pluses in them, right? That is XOR. And there's no circles with pluses here, so I should never have been thinking plain text gets XORed with this thing. It just didn't make sense. So here is how block cipher works, and this will hopefully clear up the big mess that I just made in the VOD you're watching. If you were to do block cipher encryption in, say, like a factory or a workshop setting, what you would do is you would first, of course, chunk your plain text into blocks of the block size. You'd then unbox an AES machine and plonk it on your desk. And the AES machine has 2 inputs, the plaintext input and the key input. The plaintext has to be the length of a block. The key has to be the length of, oh god, now I'm going to confuse myself again, a key. Does AES accept keys of various length, or does AES kind of implicitly hash the key before it goes in? I don't know, and I don't want to think about that right now. Point being, there's a slot for the key and a slot for the plaintext. Put them both in their respective slots, turn the handle on the machine, out poops the ciphertext. You could then think of kind of shuffling that machine to the other side of your desk and unboxing a brand new AES machine, identical to the first, putting it on your desk. Block number 2, plaintext block number 2 goes in, key number 2 goes in, turn the handle, out poops the ciphertext block. Move it to the side, fresh machine, plonk it on the desk. Exactly the same as the first 2 started off as. The third block of the plaintext goes in, the key goes in, remembering the third block of the plaintext happens to be identical to the first block of the plaintext. This machine here, turn the handle, out poops a ciphertext. And because the 2 inputs were the same, and the machine is identical, because this plain text is exactly the same as that plain text, that key is also exactly the same as this key. Spoiler alert, that machine is also the exact same as that machine. An AES machine is an AES machine. Thus, the the ciphertext that poops out is also the same. So block ciphers, you can think of them as, I mean, there's no sense if you did work in an AES factory that you'd be using fresh machines for each block. You would just put your plaintext in, put your key in, turn the handle, pull the plaintext out, put the second block in, turn the handle. But to think of them as separate machines drives home the point that these machines don't have state between blocks. It's not like as the machine gets used for successive blocks that there's like internal mechanics that are ticking over and acting differently now that we're getting towards the end. These are all, just think of them as identical, discrete, unique machines. And it just so happens when you put the same input into an identical machine as another machine, you get the same thing out. So that is how a block cipher works. I was thinking that the AES machine with the key in it was producing a stream of things that was being XOR'd with, but that would be a stream cipher, right? So that's where my kind of mental breakdown was right there with my understanding, and thus my poor explanation of how ECB works. So I hope that helps clear that up, and let's return you now to your regularly scheduled programming. Anyway, that's what ECB is. We're creating a cipher, AES with the key, the mode of ECB. So now we want this line here, yoink. Cipher is the cipher.decryptor. Decryptor.update with the ciphertext. And then we want to do decryptor.finalize. And decryptor.finalize apparently returns our plaintext. Plaintext equals that. Print plaintext. Run main. Empty string. Thanks, I hate it. Maybe this line here, maybe that plus is there for a reason. So the plaintext is the update plus the finalize. We should have trusted the code here. Cipher, AES, ECB, decryptor is the decryptor. The plaintext is the ciphertext updating the decryptor, and then we're finalizing. Stupid mouse. And we're printing. Run it. And we do get English prose. It looks like it is text, so we can decode it. Run it. There we go. We've got some funny looking noise there, but aside from that, we've got output. Now I am going to factor this out. We were kind of asked to I see that Sepkov, I'll be with you in a moment. As has been the pattern so far, I feel like we're doing this exercise so we can then use this logic in future exercises. So I will lift that logic out to its own function. Sepkov, the last part is hex. Let's not decode it, let's just print it. I bet it's what's called padding. Yeah. Because recall that I said, or just recall that block ciphers work on whole blocks, right? If we go back to our thing, block, block, block. In the case of AES 128, they're 128 bits wide. When you're doing encryption, if your plaintext is not a perfect multiple of the block size exactly right, you have to pad it so the blocks are the same size. And I'm sure that we've got an exercise coming up about padding. It rings a bell. One of the ways to pad it is PKCS 11 padding or something, I think. Rule number 1, always pad your plaintext. Even if your plaintext is a perfect multiple of the block size, add a whole block of padding. Them's the rules. Rule number 2, for however many bytes of padding you're about to add, use the number of bytes as the value of byte that you write. So in this case, the encryptor knew that it needed 4 bytes to make up to the next block. So it uses 4, 4, 4, 4. If it was only coming up one short, it would be the byte 1. If it was too short, it would be 2, 2. If the input was a perfect multiple of the block size, then it would need 128 bits of padding, which is 16 bytes. So it would be 16, 16, 16, 16, 16, 16, 16, 16 bytes of 16. That's called PKCS1 or PKCS11 padding or something like that. We'll do it in the future, but anyway, it's padding. Yeah. Cool. Let's refactor this. Let's define AES decrypt, AES ECB decrypt as taking ciphertext of bytes and a key of bytes and returning bytes. Yoink. Plop. Return. So our main function is going to do, it's going to get the ciphertext, and it's going to do get the key. Plaintext equals decrypt ciphertext with the key, and then we'll decode it and print it. Run that. Beautiful. Docstring. Decrypt ciphertext using AES ECB using the given key. We don't need parameters for that for this function. It's simple enough. Test case. Sure. Ciphertext equals open data set 1 challenge 7.text. Cool. And then I'm gonna rather let's. You thought that I was weak, boy, you're dead wrong. Let's just check to make sure that that's in the plain text. That in decrypt ciphertext with the key, which is yellow submarine, should give us true. Run the tests. Happy with that? Let's send this function to utilities, and we are done. Next challenge. Detect AES in ECB mode. So in this file there's a bunch of hex encoded ciphertexts. One of them has been encrypted with ECB. Detect it. Remember that the problem with ECB is it's stateless and deterministic. The same 16-byte plaintext block will always produce the same 16-byte ciphertext. It's the penguin problem. Yoink. Set 1 challenge 8.text. Plop. And let's grab the challenge text. New Python file. Set 1 challenge 8. Detect AES ECB.py. Do the boilerplate. Nope. Cool. Drop in our challenge text. And off we go. So we'll open that file. Set 1 challenge 8. Let's do lines equals line.rstrip. Now let's just do line for line in f.readlines. And then let's print the lines. You know what, they're not lines, they're ciphertexts. Print the ciphertexts. Run this. Nope, we're not going to do that. For C in ciphertexts, print C. Make them look pretty. Run this. Yeah, so we're getting, each line looks good to me, but you can see there's these blank lines in the middle. Because there's a new line at the end of each line that readlines is giving us. Now these are hexadecimal, so they're only going to be 0 through 9, A through F. So I'm just going to be lazy and just rstrip each one. That way it's just going to chop off any trailing white space, whether they're spaces, tabs, vertical tabs, new lines, carriage returns. You're gone. Run this, and it looks better. They're all nicely packed together. So one of these is like our penguin. One of these is going to have repeating blocks in it. How are we going to approach this? How are we going to find the line that has the repeated blocks? First thing we do, from utilities, import the chunkify function. So we can chunk these up. Block size is 128 bits, which is 16 bytes. So for ciphertext in ciphertexts, chunks equals chunkify the ciphertext into block size blocks. Print those chunks out. Aha, we've got our generator. So we'll just list this for now, and at the end we'll see if we can take the list away. Now there's a cheap way we can check to see how many unique items are in a Python list, as long as the things are hashable. So it doesn't work if you got like a list of lists, it breaks a little bit. If you got a list of dictionaries, it breaks a lot. But a list of primitive values like numbers, strings, certainly you can use this trick. So the number of chunks is the length of chunks, right? So we'll just print the number of chunks below each row of chunks. So it looks like they all say 20. There's 20 chunks in each of these ciphertexts. Cool. But how many unique chunks are in each one? Number of unique chunks is the length of the set of chunks. So now what is set? It builds, a set is an unordered collection of unique elements. So by definition, it's a set is like a list with two differences. Number one, you cannot have two of the same thing in a set. Sorry, there's three differences. Rule number one, you can't have more than one of the same thing in a set. Rule number two, everything in the set has to be hashable, so you can't go sticking lists and stuff in there, I don't think. Primitive types only. unless there's a hash function defined for the object. Rule number 3, sets don't keep order. They're like the old dictionaries. I don't think new sets are... You know what? They've probably changed that on us, haven't they? Python set ordered. Because they changed it for us with dictionaries. Yeah, I'm pretty sure you can get like third-party libraries that do give you ordered sets, but Python sets are unordered by nature. So for example, if we do set over the list 1, 2, 3, 4, we get 1, 2, 3, 4. Beautiful. If we do set over the list 1, 2, 3, 4, 4, we still just get 1, 2, 3, 4. Doesn't matter how many 4s we've got, set boils it down. It uniques it for us. There's one other really good property of a set. If we do A is that set there, if you're checking if the number 3 is in the set, that is much faster than checking if A is in a list with an asterisk on the end of that, right? Like for very short things, like a set of 4 elements versus a list of 4 elements, the list is probably faster. But if you've got 4 billion things in a list or 4 billion things in a set, putting things into a set is a little bit more expensive because it has to hash it on the way in. But after it's in the set, it's lightning fast at looking up if something is in that set or not. So it's a super cool data structure that just works beautifully for some problems. And we can use it as a really cheap way of uniquifying a list. So we print out our chunks, we print the number of chunks, and we print the number of unique chunks, which for most of them will be 20. But for some of them, I bet it will be lower than 20. Maybe just for one of them, it'll be lower than 20. Aha. This here only has 14 unique items in it. Are there any others? I'm not seeing any. Nope. Given ECB is notorious for repeating blocks whenever the same input block appeared more than once, this is our ECB entry. So based on the number of chunks and the number of unique chunks, the number of duplicated chunks equals the number of chunks minus the number of unique chunks. Tells us how many were duplicated. We don't know if it was like 6 of the same or 6 lots of 2 of the same or whatever, but yep. How do we want to approach this function? Like, I mean, now let's do it the cheap way. Let's do it the cheats way. If the number of duplicated chunks is greater than 0, that's our victim, right? Return ciphertext. So now let's lift this into a new function. Identify ciphertext encrypted with ECB. Not very creative today, I know. Block size integer by default is 16. Oh no, let's force the caller to provide it to be clear. Oh wait, we need to take some ciphertexts, don't we? Ciphertexts is a list of bytes. Let's pull in that definition of list. Yoink that. So for ciphertext is ciphertexts, chunkify it, get the number of chunks, get the number of unique chunks, figure out how many chunks must have been duplicated. And if there's any duplicated chunks, we return it. This heuristic could potentially be tweaked. Like we could have done stuff like if the number of chunks is greater than the average number of unique chunks, or average number, sorry, if the number of duplicated chunks is bigger than the average number of duplicated chunks across all these ciphertexts, then there's our suspects. But YOLO, let's just say if there's any duplicated chunks early out. Actually, no, let's identify ciphertexts encrypted with ECB in case there's more than one. So this is going to return a list of bytes. So let's have a new list. Sus, which is a list of bytes, is empty array, empty list. Instead of earlying out the ciphertexts, sus.append ciphertext, and we return sus. So if you gave this function a bunch of ciphertexts where none of them were ECB, or at least none of them had any duplication in it, you get nothing back. You get this empty list. If one or more of these ciphertexts had redundancy in it, you get them back. We should just document how that works. I'm not writing doc test for this function. I say that now. Given a list of ciphertexts, return the ciphertexts which were suspected to have been encrypted using a block cipher in ECB mode. This function assumes that any redundancy on a block basis indicates ECB encryption. So at least we're being honest about our really lazy heuristic. Now we don't need to italicize that. Actually, we do. So with open that, ciphertext equals that, block size equals that, suspected ECB ciphertexts. We'll identify the ciphertexts, with the block size being block size. Can't type. Suspected ECB ciphertexts for sus in suspected, print sus. Why am I getting a type error? We need to hex decode these, don't we? This was wrong. This was so wrong. Because these are like hex strings of length 16, which is 32 bytes. Yeah, we needed to unhexify these. Line.rstrip, aha. This needed to be bytes.fromHex over the line. See, this is why like IDEs and type hinting, like all along I've been doing things like this. Ciphertext is a list of bytes. Block size is an integer. And it returns a list of bytes. Python does not need these type hints to work. Also, Python does not enforce these type hints during runtime. But they're a lifesaver when you write them out and then later on you make a mistake. Because I didn't have this bytes.fromHex stuff. And I was getting a yellow ugliness here. If you hover over it, it says it expected a list of bytes and it got a list of strings instead. And that showed that I had a bug. So yeah, type hints. They save lives. Bytes.fromHex over that. Beautiful. Run this. We should still get the same result. Yeah, we still get the same result. We get this one line here is suspected of being ECB because it's got redundancy in it. Do we want to move this function to the utilities? That's the question. I mean, I don't love the heuristic we've given. But you know what? We should write tests, shouldn't we? Yeah, we should have a test. Everything else has a test. Let's not get lazy now. We'll write a test and we'll chuck it in the library. Just in case this challenge here is setting us up for a future challenge where it's important to do this. I'm not sure if this is just like an exercise to prove that ECB is bad and easily spotted, or if this is building up to something. So we'll chuck it in the library. Let's grab our ciphertexts for our test case. Bytes.from hex over line.rstrip for line in open. Data /s1 c8. Good. That's the ciphertexts. And now if we identify them, identify the ECBs of them, the block size is 16, we get this awful mess back. Which makes for a bit of an ugly doc string, but it is what it is. Run our tests. We got this error last time as well. Oh no. We didn't get this error last time. All these backslashes. All these backslashes cause problem in doc strings. Let's encode this to hex. No, let's encode it to base 64. That's more compact. So we just run our main function. Print base 64.b64. Pull in base 64. Run this. Grab that. Delete this, chuck it there. So now if we base 64.base64 encode that and then decode it, get rid of the B. It's looking a bit tidier at least. We should get that back. Why are you yellow? Because we need to pop one off the list. Again, type hints saving the day. You know what? I'm not happy with that. Let's grab our sus. Good. We know that the length of sus has to be 1 because we're only getting one result from this exercise. And in here, we can pop that item off the front of sus. Cool. Run our tests. Tests pass. I want to clean this main function up though. We don't need base 64 anymore. Yeah, that's looking good. Alright. Again, yeah, not the best heuristic, but at least it's got a test. At least the doc string is honest about how naively it approaches the problem. You, my friend, can go to util.py. And I think we are done with set 1. That's it. 8 challenges to the first set, and we've finished them. And I know it's a bit of a short stream tonight, but I think that is a perfect place to pull up stumps. I've had a big day. I'm feeling it tonight. But let's have a quick peek. Let's do a quick... I feel like I've done like 20 recaps tonight. Of the last 2 exercises. They were not too difficult. We implemented AES in ECB mode. And by implemented, we just grabbed stuff from the hazmat tool drawer of the cryptography library. And then we just looked for redundant chunks in a bunch of lines of hex to detect which of the lines was possibly or probably encrypted with ECB. We also polished off the breaking of our repeating key XOR. Like, it seems like all the hard work for that one was previous stream, with the Hamming distance and the chunking and the statistics and what's the nice small number that has a small interchunk Hamming distance. Like, that was a bit of a headache. After that was done, today was a dream. So set 2, what have we got coming up next? Block ciphers. So we won't do these today, we'll have a quick peek. So we're working a lot with AES, ECB, CBC, ECB cut and paste attack, byte at a time ECB decryption. So here's PKCS paddings. That's what it was, Sepkov. I'd say that those bytes of 4 at the end were PKCS number 7 padding. I think I said every number except for number 7. Implementing CBC mode, CBC bit flipping. This looks pretty cool. I'm looking forward to getting stuck into that next time. But for now, thank you very much everyone for your company this evening and your patience as we work through a couple of things. They weren't that bad though. I hope you have a good rest of your week. I'm not sure when I'll be streaming next, but when I do, I'll be posting about it on Twitter. So if you'd like to know when I'm streaming, keep an eye on that. Otherwise, hope you have a fantastic rest of your evening, and I'll catch you next time. Bye for now.